Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study principal stresses concepts, the concepts of principal stresses. What is principal stress and what is principal plane? Principal stresses are those stresses which are acting on principal planes. What is the principal plane? The planes which are on which the shear stress is zero are known as the principal planes. Now here the principal stresses, the plane carrying principal planes. Principal planes are the planes on which the shear stress tau equal to 0. So on this plane the shear stresses are 0, but the stresses will be there, that is normal stresses, or those stresses are known as principal stresses. So the plane, if it is carrying maximum normal stress, it is called major principal plane, and if the stress is the minor, then that stress is known as maximum or major principal stress. If the plane carrying minimum normal stress is known as minor principal plane, and the stress on which it is acting is minor or a minor principal stress. Now here the major normal stress which is acting, which is called the major principal plane, and the stress acting on it is called major principal stress. So here there are different cases are there in order to study. Generally, in order to study these principal stresses, this is the normal stresses are acting sigma 1 in x-axis and sigma 2 in y direction. If you turn some angle theta, that is what is sigma n and what is tau, we are going to calculate. Now that is the case study 1. If the bar is subjected to a tensile stress, pure tensile stress, if there is LL section plane, on that plane what is the load is acting? It is the P acting. The area of cross section of that LL plane is A, is area of cross section is A. There is another plane that is MM. The area of cross section of that MM plane, MM section plane is A by cos theta. So here the angle of cross section, the cross section is turned by theta angle. Now if we resolve the components along sigma n direction, the normal stress, and it is along the plane, along the section plane, it is the shear stress. Normal to the section plane, it is sigma n, that is normal stress. Along the section plane, it is shear stress. Now that normal stress sigma n, the area of cross section of this MM plane is A by cos theta. So when a uniform sectional area is A is subjected to, here it is an axial load P, then the stress acting on a cross section given by LL plane, normal to the axis, the stress here on the LL plane is P by A. But area on that plane MM, that is A by cos theta. After resolving these components along sigma n and tau or MM planes, then sigma n by sigma n into A by cos theta, that is nothing but a P cos theta. We have resolved this P, the load along normal direction, that is sigma n, and also this is the plane MM. This is the section plane LL and it is MM. Now here that is P by P cos theta along x-axis, here in this direction, that is P cos theta, perpendicular to that is a P sin theta. Now resolving the components perpendicular to MM, then it becomes sigma n times area, that is sigma n times area, that is A by cos theta, that equal to P cos theta. From this equation, sigma n equal to P times cos theta into cos theta by, that is P cos square theta by A. this is the normal stress on that section LL, or on that section. We can understand that on that section plane MM. Now there will be shear stress tau acting along the direction, that is mm, and resolving this direction, then that is P sin theta. That P sin theta is nothing but tau times A by cos theta. This is the component. Tau times A by cos theta equal to P sin theta. From this, shear stress equal to P sin theta cos theta by A. So when the stress is tensile, there will be tensile stress, tensile normal stress, and shear stress. If the load is applied compressive, if the compressive load is applied, then again compressive stress and shear stress are produced. Now the common is that the shear stress is so important. So for that we have to find out the maximum shear stress. So for that maximum shear stress, that is, we got it here now, shear stress equation, tau equal to P by A sin theta cos theta. That is nothing but P by A multiplied by numerator and denominator by 2. Then 2 sin theta cos theta, that is sin 2 theta by 2. Now when 2 theta equal to sin 2 theta equal to 1, then only the greatest value can be observed. Sin 2 theta equal to 1, then theta becomes 45. Substitute when theta equal to the greatest shear stress produced when the angle theta equal to 45. Substitute theta equal to 45, then it becomes P by 2A, tau maximum. The maximum shear stress equal to P by 2A. Now here again, let me summarize. When the rod is under pure tension, both the tensile and shearing stresses are produced. And when the rod is under compressive load, under direct compression, again both compressive and shearing stresses are produced. Now the common from under both the loads is shearing stresses. So we have to connect the shear stress is so important. Under whatever load the beam is subjected to. So so that's why the shearing stresses are more important than the applied stresses. For that, that's why we have calculated the maximum shear stress for this case study, that is tau maximum equal to P by 2 times area to A. Now what is the sigma n? The sigma n, when the beam is subjected to normal load, tensile load, then sigma n equal to P by A cos square theta. This theta is the plane cut by the plane, that is the angle making by the angle made by the plane is theta. Now that is another shear stress equal to tau equal to P by A times sin theta cos theta, that is tau equal to P by 2A times sin 2 theta. This is also another. Now the second case study is shear stresses, the stresses due to pure shearing. In before case, this is the pure tension load. Tensile load is acted on a bar. Now it is stresses due to pure tension. Now here there is a rectangular block. The rectangular block is LMNP. On this rectangular block, the shear stresses are acting tau xy direction here, clockwise. Then here, because of this tau xy, the body is under rotation, under couple phenomena. Now in order to make it equilibrium, we have used another stress, shearing stresses. Those stresses are known as complementary shear stresses. The complementary shear stresses introduces tau dash xy here. Now consider this tau dash xy with respect to tau xy. So tau dash xy into tau dash xy. Where is the tau dash xy? This is the tau dash xy times mn into ml. This is mn and ml. Okay, if we consider this tau dash xy means mn into ml, area of cross section, this perpendicular couple. The unit, the thickness of this block, rectangular block is unit thickness. Now tau into mn into ml, that is the moment, that equal to tau xy times ml into mn. Now this ml get cancelled, mn get cancelled. Then tau xy equal to tau dash xy. So both are equal. So for maintaining, for equilibrium position, so complementary shear stresses are introduced for this. Now this tau dash xy equal, and this tau xy and tau dash xy equal to tau xy. This complementary shear stresses makes the body in equilibrium. Now after getting in equilibrium, there is a plane. It is cut by a plane with an angle theta to the section that is LM. This is the AA sectional plane. Now on this plane, what are the stresses? The normal and shear stresses are going to be calculated. This, yes. Now sigma n is the normal stress and the tau is the shear stress. Along the plane is the shear stress and perpendicular or normal to the plane is sigma n, normal stress. The angle made by this plane with the LM is theta. Now what to do? We have to resolve these forces, that is stresses values tau xy and tau xy, here tau dash xy and tau xy. We resolve it along the plane of AA or LN or normal and normal to the plane of LN. Now it is normal to the plane of LN gives sigma n value, and along the plane LN resolution gives tau values. Now resolving perpendicular to AA means this sigma n, resolving it. Now sigma n into, this is the Ln, that is the length, thickness is unit, one unit, single units, that is sigma n into Ln equal to this tau xy, this is the LM. We want this component, a normal component, Lm sin theta, tau xy into Lm sin theta. Okay, this is the direction, tau xy into Lm sin theta, plus this is another tau dash xy. Here tau xy equal to tau dash xy. So you are substituted directly. So this tau xy. For this also we want along this plane. How it comes, this tau xy, that is mn cos theta. Mn is the hypotenuse, cos theta becomes adjacent side, mn cos theta. Now sigma n equal to this product, this L from left side of Ln goes to the right side and become a numerator. Now tau xy into Lm by Ln times sin theta plus tau xy into mn by Ln cos theta. Now tau xy, what is Lm by Ln? This is the Lm and it is Ln. This Lm by Ln is nothing but a cos theta, that is tau xy cos theta sin theta plus tau xy times mn by Ln, that is sin theta by sin theta times cos theta. So tau xy cos theta sin theta plus tau xy sin theta cos theta, both are equal. That means 2 times tau xy sin theta cos theta. Tau xy times 2 sin theta cos theta, that is sin 2 theta. This is sigma n equal to tau xy times sin 2 theta. This is what we resolved perpendicular to the cross section or perpendicular to the sectional plane AA. Now here, in order to find out the maximum value of sigma n, when theta equal to 45, then it becomes a sigma n equal to tau xy. And minimum, when 2 theta equal to minus 90 or theta, then it becomes sigma n equal to minus tau xy. Negative tau xy indicates the compressive, whereas the positive tau xy gives, or positive sigma n value gives a tensile value. So this is the meaning of here, this is the meaning of the equation. What is the meaning of the equation? The normal stress equal to tau xy times sin 2 theta. Now, after this, we have to resolve parallel to the sectional plane AA. Now it is perpendicular over, that is sigma n. Now parallel to the sectional plane tau. This is tau into ln. Downwards means positive. That is tau into ln times units, single units. The tau into ln equal to tau xy times we want lm cos theta downwards. That is mn cos theta. Where is mn? This tau xy times they consider here. Tau xy, this component, that is tau xy into mn cos theta. Sorry, tau xy times mn. We want along the plane mn sin theta. This mn sin theta gives positive. Tau xy times mn sin theta minus tau xy times lm cos theta. Now again, tau equal to tau xy times mn by ln sin theta minus tau xy times lm by ln cos theta. This mn by ln is equal to sin theta into sin theta sin square theta minus tau xy times lm by ln means cos theta. Tau xy cos theta times cos theta. Now tau xy sin square theta minus tau xy cos square theta. So make it common term, that is tau xy times cos square theta sin square theta minus cos square theta. That becomes negative of cos 2 theta, that is minus tau xy cos 2 theta, that equal to tau. Now this is the shear stress acting along the plane AA, sectional plane. When tau will be 0, when theta equal to 45, cos 2 times 45, cos 90 equal to 0. The shear stress equal to 0. Now this is the plane on which that plane is known as a principal plane. That's why the shear stress become when theta equal to 45, that plane. When theta equal to 45, the shear stress becomes 0. That plane is known as the principal plane. On that plane, the stress is obtained is known as principal stress. Now sigma n is the principal stress, that is tau xy sin 2 theta. When theta equal to 45, that means when theta equal to 45, that plane is known as the principal plane, on that principal plane the stress obtained is known as the principal stress. Now here, when theta equal to 45, then sigma n equal to tau xy. This is sigma n equal to tau x. This tau xy is the complementary shear stress. The shear stress acted. Okay, that's why this is the case comes under the category of pure shearing. Now the third case is that two mutually perpendicular direct stresses are acting on a cube or on a triangular element. Now it is the triangular element actually when the load is acting on a body, that location is considered as a triangular location here, that is LMN. Now when this LMN triangle, it is making an angle theta. Now there are two stresses are there, mutually perpendicular means sigma x and sigma y. The normal stress along axis x is the sigma x and normal stress along y direction is known as sigma y. Now it is the plane ln. On that plane we have to find out the effect of these two stresses, normal to this plane and parallel to that plane. Normal to the plane ln is known, gives the sigma n, and resolving parallel to the tau, parallel to ln gives shear stresses. Now how to resolve it? Resolving normal to the plane ln. This is the ln plane. This is sigma x and it is sigma y. Now sigma n into ln, sigma n, and it is the tau. Sigma n into ln equal to sigma x times the sigma x normal to that means sigma x sin theta, sigma x sin theta, and the cross section, that is lm. Sigma x, where is that sigma x? This is sigma x and sigma y. Yes. Now it is sigma x. We want what is the normal to that? Sigma x into lm cos theta plus sigma y times mn sin theta. Sigma y times that is mn sin theta. Now sigma n equal to sigma x into lm by ln times cos theta plus sigma y times mn by ln sin theta. Now if you make it lm by ln equal to cos theta into cos theta, that is cos square theta. Sigma x times cos square theta plus sigma y times this mn by ln from this triangle LNLM, from the triangle mn by, where is that mn? This mn by ln, that is sin theta. Now it is sin theta times sin theta sin square theta. Sigma x cos square theta plus sigma y sin square theta. Then it becomes sigma x by 2, make it 2 cos square theta plus sigma y by 2 sin square theta. Now sigma x by 2, this 2 cos square theta can be written as 1 minus sin square theta plus cos square theta plus, that is plus sigma y by 2 1 minus cos square theta plus sin square theta. Now here sigma x plus, make it division here. Cos square theta can also be written as, okay, another term, that is here we have written as 1 minus sin square theta plus cos square theta. Sigma x by 2, that is becomes 2 cos square theta plus sigma y by 2 sin square theta. After simplification, sigma x plus sigma y by 2, from this here sigma x by 2 and here sigma y by 2. Sigma x plus sigma y by 2 plus sigma x times cos square theta minus sin square theta by 2, okay, plus sigma y times cos square theta minus sin square theta by 2. Now further simplification, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta. Now here it is the sigma n. This is the equation sigma n, that is normal to the plane Ln. Now here further simplification, when theta equal to 0, sigma x plus sigma y by 2 cos 0, 1, sigma x minus sigma y by 2, that is nothing but 2 sigma x by 2, that is sigma x. When theta equal to 90 degree, when 2 theta, that is theta equal to pi by 2, then what will happen? This is the value, sigma y happens. When theta equal to 0, it is sigma x, sigma n equal to sigma x. When theta equal to pi by 2, then it becomes sigma y. Now next we have to resolve parallel to Ln. That resolving parallel to Ln plane gives shear stress, that is the tau. The tau into Ln equal to Ln. This is the, okay, parallel to the planes. That is sigma x into Lm sin theta minus sigma y times cos theta, that gives the tau sigma y cos theta times mn cos theta. See, this is mn. Now here sigma x into Lm by Ln sin theta, this Ln goes right side, Lm by Ln as in denominator, sin theta minus sigma y times mn by Ln cos theta. Now sigma x, this Lm by Ln equal to cos theta, mn by Ln equal to sin theta. Substitute here in the place of Lm by Ln and mn by Ln, that is sigma x cos theta sin theta minus sigma y sin theta cos theta. Make it common sin theta and cos theta, it becomes sigma x minus sigma y sin theta cos theta. It is nothing but numerator and denominator multiply it, then sigma x minus sigma y by 2 times sin theta cos theta, that is sin 2 theta. This is the shear stress equation on a plane Ln. Now, the maximum value of tau occurs when 2 theta equal to 1. The sine 2 theta equal to 1. That is 2 theta equal to pi by 2 or theta equal to pi by 4. And then it becomes sigma x minus sigma y by 2. And the resultant stress, this is the tau maximum. Okay. The tau is this is the value tau. The resultant stress sigma r equal to under square root of sigma n square plus tau square. This is the sigma n value and it is the tau value here. Substitute here, then it gives the resultant stress. Now after getting resultant stress, we have to know the direction of that resultant stress. The direction of resultant stress is tau tan phi equal to tau by sigma n. Tan phi equal to tau by sigma n, where phi is the angle made by the shear stress. Okay, that is normal to the plane. This angle is known as angle of obliquity. That angle is known as angle of obliquity. Now here again, here this is the case of when pure direct stresses, both x and y are acting in x direction and y direction. Along x direction it is sigma x and along y direction it is sigma y. Okay, this is sigma x and sigma y. There is no shear stress, it is not acting. Now in this class we have studied there are three cases. One is in unidirectional tensile stress is acting, that is called pure tensile. That is called stresses in a tensile member, only pure tension load. Okay, it gives only unidirectional stress, normal stress, that is sigma. Another one, second case we have studied is the pure shearing. What is the pure shearing? Tau xy is acting. There is no normal stress on this case study. Okay, the third case study is that the two direct stresses are acting in mutual perpendicular. That is sigma x and sigma y. This is sigma x and sigma y. For these case studies, we found what is sigma n and tau values. For case 1, sigma n equal to p by a times cos square theta and tau equal to p by 2a sin 2 theta. But shear stress making a maximum role, then we found out the maximum shear stress is produced is tau max equal to p by 2a. For the case 2, that is pure shearing. For pure shearing, sigma n equal to tau xy sin 2 theta. And here on this plane, when theta equal to 45 degrees, the shear stress becomes 0. That's why that plane AA is known as the shear principal plane. Now the third case, the two mutually perpendicular direct stresses are acting on the planes, on the sides LM and MN. For that, what is sigma n? The sigma n value is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta. And the shear stress equal to sigma x minus sigma y by 2 sin 2 theta. So this is the tau. For this case study, the tau equal to sigma x minus sigma y by 2 sin 2 theta and sigma n equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta. Under the square root of sigma n square plus tau square gives the value of resultant stress. This is the magnitude of the resultant stress. And what is the direction of the resultant stress? That tan phi equal to tau by sigma n. This phi gives the angle of obliquity. So that means the angle phi where the resultant stress makes with the normal to the plane. The angle which the resultant stress makes the angle with normal to the plane. With the normal to the plane, that is known as the angle of obliquity. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.